we are going to discuss how the quantum mechanics evolves, and the very inception of the quantum mechanics will be discussed in this class. And for the prerequisites, that is our previous knowledges which we have regarding the quantum mechanics, is the de Broglie hypothesis, then the Heisenberg uncertainty principle. As you know, the Heisenberg uncertainty principle is the very birth point of the quantum mechanics, and you have all the classical mechanics idea regarding the dynamical systems, and I am starting from that point of view. And the basic postulates of quantum mechanics, let us take first look on that. Every dynamical variables, every dynamical systems are represented by the position and the momentum of the system. If you know the position at the time t and the momentum at the time t, then you can tell every dynamical variables of the system, that is force, that is pressure or energy or etc. There are some different dynamical properties there in case of classical mechanics. But in quantum mechanics, as Heisenberg told, that you can't point out a definite position or the definite momentum of a particle, of a moving particle at any instant of time. The position is if you talk about the position, then it will be consisted of some uncertainty in position delta r and the momentum delta p. The uncertainty is there, and the product of them is equal to h cut. That is, this minimum uncertainty is God given, and this is the law of nature. So you can tell the particle is at this position at this point of time. We can definitely specify a particle, rather a quantum mechanical particle. So quantum mechanics in broad point of view can be applied in atomic physics, in nuclear physics or particle physics, or in astrophysical interests. So in our everyday life we can tell that yes, my mobile is at the tabletop at this point. You can say yes, it is definitely there. But in view of quantum mechanics, you can tell that electron is at this point, at this time, moving electron. I am talking about the moving ones. The moving electron is at this point, at the point of time, say t is equal to t. We can tell the uncertainty is there always. So the some question arises in quantum mechanical point of views which needed to be answered. Now the first question is how a quantum state of the particle is mathematically described at the time t. In case of classical mechanics, it is written over here, the position and the momentum at the point of time t, it is written over here. But what is the state of the particle at time t in quantum mechanics? It is needed to be answered. And how to calculate the physical quantities, that is the energy, say from this quantum state. And the important next important question is, you know the state of the system at t. So what will be its state at the latter time t prime? So these answers are wrapped up in 6 postulates which I am going to describe. The first postulate is wave function postulate. The answer is that the state of the system, the quantum state of the system, is described by a function which is called the wave function. And the wave function is not a physical thing, it is just a function. Some properties are there. The function should be single valued and square integrable. Some mathematical point of views are there, but physically the wave function cannot be experimentally verified. Okay, the wave functions are function of position and time, that is x, y, z and t. The function is depend on, but the what we have get physically, say the function is psi xt in one dimension. It is a single valued function. Probability amplitude it is called. Why? Because psi star psi gives the probability of finding the particle at x at time t. Psi star psi means psi star is the complex conjugate of the function psi, and psi star psi you can write it as mod psi square also. This gives the probability of finding the particle at the position x at that instant of time t. That is why psi is called the amplitude. Okay, amplitude of probability. It is called wave function, or sometimes it can be called as the probability amplitude at any instant of time t at the position x. So this is the physical interpretation of the wave function. That is, the mod psi square will give you the probability of finding the particle, because I have told you that according to Heisenberg uncertainty principle, you can tell that the particle is at this point at the instant of time t definitely. So there should be an answer in probable way that probably the particle is at this point. So probability is the main thing which can be calculated throughout the quantum mechanics study. The second postulate is the operator postulate. Every dynamical variable such as position, momentum, energy, the dynamical variables have some operators. Say a dynamical variable q has the operator form capital Q, and the operator will also satisfy, every dynamical operator should satisfy the eigenvalue equation, which is written over here. This is the eigenvalue equation, where q is the operator form of the dynamical variable, psi n is the nth wave function, qn is the eigenvalue corresponding to the wave function psi n. Wave function is you can call wave function as eigenfunction because this equation is familiar to you. This was in a matrix equation. Matrix can follow the eigenvalue equation, and here the eigenvalue is qn because the wave function is reproduced by operating the operator q on the wave function, but with a multiplicative constant qn. Here qn is called the eigenvalue, and psi n, the wave function, are often called the eigenfunction corresponding to that eigenvalue qn. Okay, so this is the second postulate of the quantum mechanics. So new things are there with respect to the classical mechanics. Classical mechanics don't need any operator point of view. The operator point of view comes into play when you are talking the dynamical variables in case of the quantum mechanics, and also the eigenvalue equation is there. This eigenvalue qn is experimentally verified. Okay, so from the experimental point of view, the eigenvalue equation is very much important. I will come into that in the latter half of my class. And the the operators should follow the Hermitian property. Hermitian property means if an operator satisfies this equation, this kind of equation, where psi a is psi and psi b are the two wave functions of the system, that is the two states. There are several states of the system. What do you mean by the state? Let me explain that. Let us suppose Earth is revolving around the sun, so it will follow an elliptical trajectory. So each point on the elliptical at a given time are the states of the Earth. It is a classical point of view, but in quantum mechanical point of view, at each time the Earth will assume some wave function. So in due course means in the motion of the Earth, the state of the Earth changes. It resides at some time at apogee, it sometimes resides at the perigee. So the states are different. Sometimes the earth gets closer to the sun, sometimes it is very much away from the sun. So those states are represented by psi's, different psi, different wave functions in case of quantum mechanics. If we assume that the earth is a quantum mechanical particle, okay. So this psi a and psi b are two different states of the particle, and if integration psi star a q psi b dr is equal to the integration of q psi a whole star into psi b dr, then this operator q will be called the Hermitian operator. It was also seen in case of our matrix algebra, the Hermitian properties there, but there are dagger signs were used. So Hermitian terms you know, and because Hermitian matrices, from the mathematical physics I am talking, because the Hermitian matrices have real eigenvalues. Here the operator q is representing a dynamical variable, and the values of those dynamical variable is, if experimentally determined, then it will give you a real value, because you are doing real experiments. So the dynamical variables will give you a real value, that is electron is at 5 centimeter distance from the nucleus, so 5 nanometer I should say in the atomic picture. So the real values are coming out of the experiments, and the operators are the representer of the dynamical variables. So the operators eigenvalues should be real, because the operators are consistent with the dynamical variables. So the eigenvalues of the operators should be real. That is why the Hermitian properties come into play to represent an operator in quantum mechanics. Okay, but the property of Hermitian, that is the Hermitian operators, will follow this equation. This equation is very much new to you, so remember this. The next one is basis set postulate. What is that? This is a simple eigenvalue equation which I have talked over here. Psi j is the jth wave function, jth state. J means j can be run from 1 to infinity, say. So any one of its state j, say jth state, the wave function of the system is psi j. So the eigenvalue equation of the operator q is q psi j is equal to qj psi j. Qj is the eigenvalue which can be determined in practical examples. Now the total state of the wave function at any time can be think of the superposition of all those states, that all those infinite number of states, that is the whole state of the net state of the wave function of the system can be written as the superposition of each of them states multiplied by some constant Cj. Okay, that is Cj psi j, sum over Cj psi j will represent the actual wave function of the system at any time, any point of time. Why? Because the particle in quantum mechanical, the quantum mechanical particle can be found in any of these states at a given point of time. That means, let us take an example. As you are studying now, you are at your home or you are at your study place, but you are not watching a movie in Netflix. You are not playing at the ground, but quantum mechanical pictures says that yes, you are doing simultaneously both, simultaneously studying, watching a movie, playing in a ground. This is the quantum mechanical picture. That is, you can be found in your study room, as well as at this time you can be also found in the playground or watching a Netflix movie. Okay, so these are very much different point of view from our everyday life experiences. That is very much departure from the classical mechanics. So this departure can be formulated mathematically by this basis set postulate. Okay, so psi, the whole state of the system, can be represented by each of the states by adding them, by multiplying some constants with them. These constants Cj can be real, can be complex in nature mathematically. So this will be discussed in great detail in our latter half of our class. Fifth postulate is the expectation value postulate. This is the real one. Experiments can be done on the quantities. So experiments are the real results you have in your hand. Okay, so experiment doesn't know whatever the results are coming from quantum mechanics or from classical mechanics. Whichever mechanics is best suited to justify your experimental results, it can be said that the system is classical or quantum mechanical. Okay, so in classical point of view, the results are there in very much so in complete certainty. You can deduce dynamical variables such as position, momentum, energies. So it will be tallied with the experimental results. So you can tell that the results are coming out of during by the classical mechanics. But what about the quantum mechanics? How the quantum mechanics justifies those experimental results? Answer is the expectation value formula. Here Q is the dynamical variable which you want to verify experimentally. So the expectation value of Q is equal to the integration over psi star capital Q psi dr, where capital Q is the operator form of that dynamical variable small q, and psi is the state of the wave function, which can be again described as the basis set formulation or can be any one of the state. So this is different question, but I want to describe you how the measurements are done in case of quantum mechanics. Answer is the expectation value formula. Here by doing this integration you can get a value corresponding to the dynamical variable Q, and this value should be consistent with the experiment. Okay, and the sixth postulate is the time evaluation. So you have the wave function, that is the state at a given point of time. What is the state of the system at latter point of time? That is, the wave function should vary with time, and the equation responsible for the change or the time evolution of the wave function is this. This is actually the time dependent Schrodinger equation, where h psi is equal to I h cut del psi del t. H cut is the reduced Planck constant, that is h by 2 pi, and capital H is the Hamiltonian operator, means kinetic energy and potential energy together form the Hamiltonian function. We know this from our classical mechanics, but here the Hamiltonian is an operator because potential energy and kinetic energy are also dynamical variables, so they also be described by an operator, by operators. So by adding kinetic energy operator and potential energy operator, you will get the Hamiltonian operator. And if Hamiltonian operator operates on the psi, that is the state of the system, wave function of the system, is equal to, gives you I h cut into del psi del t. Solving this equation, you can find the psi as a function of both x, y, z and t. Okay, so psi can be found out found out from this equation. Let us take a look on the probability density. What is that? I have told you that Max Born interpreted the wave function, which is psi, a single valued wave function, and the mod psi square of that will represent the probability density of the particle. That is the probability of the particle per unit distance, per unit area, per unit volume, whatever the dimension you use, it will give you the probability density. So let us take a volume dV. We wish to find a quantum mechanical particle within this volume dV. So what will be the probability of finding the particle within dV? Answer is mod psi square into dV. Okay. So if one integrate this mod psi square dV over the whole space, that is over the all taking the universe, the result will be 1, because this is your probability of finding the particle within a small volume. If the integration is done over this quantity throughout the space, the answer should be 1, because the probability of finding the particle in the universe should be 1. Let us suppose you have a 5 rupees coin in your pocket and the coin is lost. So the probability of finding the coin in your pocket is 0, but the probability of finding the coin in the universe is not 0. If it is stolen, that it will be found in else's pocket. If it is lost in your say in your school, in your college, then it will be found there, but it is somewhere in the universe. Okay, so the result should be 1, the integration should be 1, and then the wave function, if any wave function satisfy this relation, then the wave function psi is to be called the normalized wave function that is normalization to the unity, normalized to unity. Okay, these terms are often used in quantum mechanics, so be serious with those terms. Now the superposition principle is discussed here. The superposition principle is nothing but the basis set expansion, where I have told why basis set expansion is there. This is the basis set expansion is the C1 psi 1 plus C2 psi 2 dot dot dot, so many terms are there. So this is a kind of superposition principle, as you have seen in your physical optics. Say in case of interference experiment, the lights coming from two coherent sources gets get superposed on the screen to give you the interference patterns. So there are superposition principle. There superposition is happened on the field vector, that is the electric field vector of the light wave, but here the superposition is taken on the wave function. Okay, in case of quantum mechanics, obviously, and C's are the constants. The significance of C's will be discussed in later talk, in my later talk. So I am not going into details. For the time being, just assume the C's are just constant, whether it may be real or it may be complex in nature. Okay, so let us take the very interesting and very much important difference between the classical and quantum probability densities. For this, let us take an example. A system consisted of two states, that is two level system is there, psi 1 and psi 2. Two states are possible. For example, you can think of an electron which is moving in space, which has upspin and downspin. So upspin is represented by psi 1 and a downspin state is represented by psi 2. What is the superposition principle? The total quantum state of the system can be written as psi 1 plus psi 2. See, it is just like C1 psi 1 plus C2 psi 2, but C1 C2 are assumed to be unity here. for the sake of our calculations or simplicity of our calculation, I have written 1 in place of C1 and in place of C2. So superposition principle gives us the total wave function psi as psi1 plus psi2. Now the probability density of finding the system in one state is mod psi1 square, and probability density of finding the system in second state is mod psi2 square according to Max Born interpretation. So if one talking about the classical probability density, then classical mechanics, as the spin up and spin down are two independent phenomena. So what is the probability of finding the electron or the system in any of the two states is the sum of the individual probabilities. That is the probability theory. You are familiar with coin toss problem, that is head is consisted of half probability and tail is consisted of half probability. So the probabilities of being head is half, probabilities of being tail is half. But if one asks you that what is the probability of being head or tail, that is a system can be found in any one of its probable states is just sum of those, that is 1. The coin should be found in head or tail, that is any one of the states. The probability is greater than each probability, so P1 plus P2 is there. But in case of Born's probabilistic interpretation in quantum mechanics, the quantum mechanical probability PQ is the mod psi square, because now the quantum mechanical state is a superposition of those states. Psi1 and psi2 can be seen together. Your head and tail cannot be found together. Okay, as I have given the example of yourself, that you are studying at the time, not only studying, you are watching the Netflix movie, you are playing in the ground according to the quantum mechanical state. All states, whatever you do, whatever you want to do, are the probable states, and the state at any instant of time is a superposition of those states, those wave functions. Okay, and so the psi is the state of the quantum mechanical system. So the probability of finding the system in any one of the two states is mod psi square, not mod psi1 square plus mod psi2 square, mod psi square. So what will give the mod psi square, that is psi1 plus psi2 whole mod square, that means psi1 plus psi2 star into psi1 plus psi2. So it will give you 4 terms, mod psi1 square plus mod psi2 square plus psi1 star psi2 plus psi2 star psi1. So this is very much different from P1 plus P2. That is not equal to P1 plus P2. That is PQ, quantum mechanical probability, is not equal to the classical probability. So this is the very important and very basic difference between the quantum mechanical and classical mechanical point of views. Now the normalization. What is called normalization? Normalization is a constant. Suppose you have a wave function psi, any function psi, which is single valued. So if you multiply that function by n and you call it an actual wave function of the quantum mechanical system, that is psi n is equal to n psi, then the square integration of the psi n throughout the whole space should be 1. Here, for the sake of the simplicity, I am considering only the one dimension motion of the particle. So minus infinity to plus infinity means the whole space integration over psi n square dx should give you 1. So if you put the value of psi n, then n square will be come out of the integration. N can be complex also, so mod n square is written over here, So mod n square integration minus infinity to plus infinity psi square dx is equal to 1. So what is n mod n square? It is 1 by integration minus infinity to plus infinity mod psi square dx. So to get the value of n, that is, n is called normalization constant because it is coming from the normalization condition. That is why n constant. So n can be found from this equation if the square if this integration is done. So to integration to do this integration, the mod psi square, that is the integrand, should be integrable. That is why another condition over psi is imposed on, that is, we have seen that the wave function should be single valued. Yes, it was there in the postulate, but another quantity, that is the mod psi square, should be again the square integrable. That is, mod psi square should be integrable. That is, psi is the square integrable function, should be square integrable function, because it is related to the normalization constant, and normalization constant is related to the wave function of the system. So psi square should be square integrable. That is, the wave function is also square integrable function. So these are the important formula also. And orthogonality of wave function is another important property. Say you have two different functions, wave functions, and un. If star un dx integration from a to b, a and b are the interval within which the wave functions are defined. So the integration is from a to b over star un dx. If it is 0 for n not equal to n, then u functions are called orthogonal functions. Okay, these important features can be used in the latter half of the quantum mechanics. Now let us take some examples. Before going to the examples, let us summarize what we have learned. We have learned basically 6 postulates of quantum mechanics, from where the quantum mechanics started. And from those 6 postulates, the first one is the interpretation of wave function, second one is operator, and the third one is the property of operators, which should be Hermitian in nature, satisfying this equation. Those 3 are basically mathematical point of view, and the fourth one is the physical point of view, which is basis set expansion. It is related to the probability, and the expectation value, fifth one, is directly connected to the experiment. This is the real one. One has to find the expectation values of every dynamical variables under quantum mechanical point of view. And sixth one is the property of wave function and development of the wave function with time. As time passes, what are the changes in the wave function? The answer is this equation. You solve this, you will get the psi as a function of time exactly. Then the probability density, superposition principle, and the difference between classical and quantum mechanical point of views are discussed, followed by the normalization and the orthogonalization properties. Now let us take an example. Here in the problem, it is told that the system is found in the wave, a quantum mechanical system, moving particle, has wave function psi n is equal to this. Psi n is the nth state wave function. For this case, let us assume that n is equal to 1. So one state, at the 1th state, the wave function can be written, and Lz is a dimension of length having 1 nanometer value. So the question is, what is the probability of finding an electron, that is the particle, quantum mechanical particle, between the length 0.1 to 0.2 nanometer. Okay, For this we will use the Max-Born interpretation or the postulate of the quantum mechanics, that is the probability is the square integration of the wave function from the limit point 1 to point 2, because the question asked in this limit, so we have to integrate throughout this limit. So the integration is very much straightforward. The sine square will give you 1 minus cos 2 theta, so integration can be done. Result will be 0.042. There is a probability of finding the particle, that is the electron here, between the length 0.1 to 0.2 nanometer is 0.042. That is the chance of getting the electron in this region is 4.2%. Okay, let us take another example. Another wave function is given, a cos 2 pi x by L, where the wave function is defined in the region minus L by 2, L by 4 to plus L by 4. That is, a particle outside this region is not admissible. Let us first find the normalization constant A. Then the question is, what is the probability of finding the particle in the region 0 to L by 8, that is half of the right hand side region. Okay, so first concentrate on the normalization constant and start from the normalization formula, that is mod psi square dx is equal to 1, minus infinity to plus infinity, because the our problem is one dimensional. So there is no point of integration from minus infinity to plus infinity, because the wave function is not defined outside the region minus L by 4 to plus L by 4. So this integration should be boils down to minus L by 4 to plus L by 4. Put the values of psi, it will give you a square which is come out of the integration, and this integration can be done very easily, and a is equal to, do it by your own, and a will be find out that a square is equal to 4 by L. So the second part, what is the probability of finding the particle between 0 and L by 8 distance in the right hand side of the region? So integration should be not done over the whole space, it should be done on 0 to L by 8. So you know the psi now, you know the A, put all those things and do the integration. You will get the result 0.41, that is 41% of getting the particle in the region 0 to L by 8 as the particle moves within the limit minus L by 4 to plus L by 4. Okay. The last problem I will discuss over here. Let us consider the box of length L where a particle is confined, a ball is confined, and the ball can be moved in the left hand side and the right hand side, but it can't escape the walls of the from the box, that is it cannot move over here and cannot move greater than L distance. So what is the question is the find the probability of finding the ball in the left half of the tube at any time, at that time, at any time. The answer is very much simple. As the ball is moving here within the box, so the probability of moving the ball towards our left is half, that is 50% chance of the ball to move in the left side. That is your classical idea tells you. Is the quantum mechanical idea is consistent with that idea? Let us check first. So the wave function, the picture of the wave function is given, the wave function is given. Okay, the wave function is constant c, the constant is not known, the constant is there, the wave function is constant throughout the region 0 to L. So the probability interpretation will tells you that mod psi square dx should be 1 from minus infinity to plus infinity, and in place of psi you have written, psi is missing here, there is a printing mistake. So in place of psi you put c, so mod c square dx is equal to 1, and the region is 0 to L, so minus infinity to plus infinity integration will be boiled down to 0 to L integration, and from here c can be found out as root over of 1 by L, simple integration is there. The question is, what is the probability of the ball to move in this region 0 to L? 0 to L by 2, latter half, first half of the box, that is from 0 to L by 2. So integration over mod psi square dx to be done from the limit 0 to L by 2, and you know the wave function at this time, because C we have found, and put those C and do the integration, you will get 0.5. So 0.5 means the probability is half, that is 50% chance from the quantum mechanical point of view that the particle will move towards the left, which is very much consistent with the classical idea. So you see the cases where the classical ideas can be applied, the quantum mechanical results is very much consistent with the classical idea. So let us stop here. So we in this class we have discussed, mainly focused on the probabilistic interpretation of the quantum mechanical point of view. So thank you for listening.